like
helping
that,
40
you?
students.
You're famous,
You
Miss
should
Russell.
monetize them.
Yeah, I'll get a penny a year. Yeah. All right, so today we're going to be doing 4.6a, which is related rates part 1. The numbering and the labeling is going to be weird for this one because I added like an extra lesson in between some of them. So you guys might be like, why is there a part 1, day 2, and day 1? It's because I added it in at the end of the fact, okay? So that's why.
Wait, what?
All right, you don't know about it yet. You'll see next time. All right.
Oh,
So step 1 is we're just going to practice because in related rates problems, the rate of change of one or more quantities is given, and we're asked to find the rate of change of another quantity. So that's going to be our goal when we do related rates problems. So step 1 is we're going to have to be able to differentiate any function in terms of dt, okay, in terms of t. So in terms of time. So what would be the derivative of s?
ds over dt.
Good, ds dt. And then as you can see, 4 pi is a constant. So what's the derivative of r squared?
2r.
Good, so that's going to be 8 pi times r times
dr over ds.
dr over dt. Remember, everything's in terms of time. So
Wait,
this
did you
one,
need to ask what the derivative of r was?
yeah, we did it.
Okay, I was just making Oh, okay, I was just making sure.
So we did the same one yesterday. You might have to, did I give you notes over there? Yeah, I did, okay. So this one you did yesterday, it's just going to be 2 times dx dt plus, go ahead.
Would it be 2x? What would it just be?
Oh, you're right. Yeah, I don't know why I did that. 2z times dz dt. So that's implicit differentiation in terms of time. And then what about the last one? dv dt equals. What's going to happen on this one?
Product rule.
Good. So I'm going to bring the constant out front. And I'm going to do the product rule inside of the parentheses. So what's the derivative of r squared?
2r.
Times?
dr over dt.
Good. Times the other variable. Plus the derivative of the other variable, which is? 1 times?
dh over dt.
Good. Times the other, which would be r
r
squared.
to the second power.
So that is implicit differentiation using the product rule because we have 2 different variables. Okay. Now here's what the good news can be with some of these problems. Sometimes if a rate is constant, you can actually plug it in before taking the variable and then you have one less variable to worry about. So we'll talk about when that comes up. So these right here are going to be your guidelines and steps to related rates problems. You're going to see these on almost all the notes throughout. I just put them on there just to refresh your memory. So you're going to read the problem and you're going to draw a picture. Okay? Drawing a picture is not an optional step. I'm either going to give you a picture or you have to draw a picture. There's no way around not drawing a picture in these problems. Does everybody understand? Doesn't have to be an artwork. It just has to be a sketch of some sort. Label all the quantities. So you're going to label the ones that you want to know and the ones that you already know. Okay? Find the equation that is going to relate these quantities. So if we're talking about 2 sides of a triangle, we're trying to find the third side. That may be Pythagorean theorem. If we're talking about an angle between 2 sides in a triangle, that's going to be the sine, cosine, tangents. Simple geometric facts, so that's like all the area, the volume formulas. Now, I will provide these for you on the test. I may not give them to you for that specific question, but I'll give you a list of them so you know what they are and when to use them, okay? And that's the main ones that we're going to look at today. And then with geometry, also proportions, okay? Proportional things that are similar in shape, okay? And then we're going to differentiate with respect to time and solve an unknown rate. Now, this is really important. If a quantity is constant throughout, you may substitute into the equation prior to taking the derivative. So an example of this I can provide for you is one from yesterday. So do you guys remember yesterday we talked about that ladder sliding down the house? Yeah. Now, when the ladder slides down, those 3 sides of the triangle, this gets shorter, this one gets longer, but does the ladder ever change length? So that would be like a constant that you could plug in prior to taking the derivative. Now, sometimes you're going to have to plug in the constants beforehand because then you won't have as many variables to solve for in the end result. Okay? All right. That just depends on the problem, though, and we'll talk about how to address that. So the first problem we're looking at is a spherical balloon is being pumped with air at a rate of 8 feet cubed per minute. How fast is the radius changing when the radius is 0.5 feet? So, this right here is the rate of which what changes?
The balloon's radius changes.
Well, the balloon's radius does change, that's correct, but this rate they gave me isn't the radius, it's the what?
Volume?
The volume. So the reason I knew it's volume is because it's what? The units, right?
Well, it's also being pumped up, so it's being
Exactly. You can think about it contextually or look at the units. That's going to be volume. Does everybody see that? So you have to determine if each of the variables, what it is, not only what it is, but if it's a value or it's a rate of change of that variable. So as you can see, this one is a rate of change of that variable, not just a value. So this is dv dt. This is the volume with respect to time. So does everybody see how I knew that was volume with respect to time? And not just regular volume. Volume wouldn't have the minutes on there, okay? And the way they say it, the rate. These are rates. Rates are always going to be d something over dt. How fast is the radius changing? The radius changing, is that a rate or a value?
a rate.
Rate. What would be the rate of the radius changing? How would we denote that? dr over dt. This is what we want to know. And then they're just telling me what the radius is. Is that a rate or a value?
It's a value.
So r equals 0.5.
Point.
So now what we're going to do is we're going to look through and think through this problem. There's only two variables in this equation, volume and radius, correct? Those are the only two things that could change. If you are expanding a balloon by pumping it with air, is either the volume or the radius going to stay the same at any point?
No.
No, they're both changing. So what that means is you can't plug any values in prior to taking the derivative.
Yeah.
So if anything would stay the same, then you can, but if it won't stay the same, you cannot. Okay? So that means that we're going to go ahead and take the derivative of this. So that's going to be dv dt equals 4/3 pi times, what's the derivative of r cubed? 3r squared times dr over dt. What's going to happen with these 3's?
They're going to cancel out.
They're going to cancel out. So we're left with dv dt equals 4 pi r squared times dr dt. Everybody good with how we got that? Now we're going to go through and see what we can plug in. So I can plug in 0.5 for the radius. What else can I plug in?
Your dv dt.
dv dt, which is going to allow me to solve for
Your dr dt.
dr dt, because now I have one variable left, and that's always your goal. So we're going to plug in. So that's going to be 8 equals 4 pi 0.5 squared times dr dt. That gives me 8 equals, this becomes 0.25 times 4 is 1, so it's just pi. And you're going to notice I sometimes drop my units and put them in at the end. I just find it easier. So then what would be my last step to find r dr dt by itself?
Divided by pi.
Good. So just make sure you read the question and see if it wants it in terms of pi or a decimal approximation. We're going to leave it in terms of pi today. It's just easier. And then now we have to talk about units. So it's going to be the radius with respect to time. What would be the units for the radius? Feet,
Feet.
but it's with respect to time, so it's feet per what? Minute. So any like length of any sort is going to be that unit without squared, anything like that. Anything that's an area is going to be squared, and anything that's a volume is going to be cubed.
I have a question.
Sure.
With taking the derivative of that volume,
Yeah.
can you just bring the 3 to the 4/3? Because
Yeah.
it would give you the same thing.
Yeah, totally. I would just, the reason I didn't do that step, jump to, if I were doing it in my own time, I would, but I just wanted to make sure that I didn't lose anybody with what happened.
'Cause, yeah,
More of a
I was-
teaching thing.
because I did something like that earlier where
Yeah.
if you did 4/3 and then I moved to 3,
Yeah.
it just gave you 4,
Yeah.
and it would just be r.
Yeah. Yeah, you'll notice, like, I cut corners when I do it myself, but I won't do that when I'm teaching it, just because I know I'm going to lose people with what's happening. So just, it's more so, like, so you can see I took the derivative, and you didn't get lost in what I was.
Okay.
Yeah.
That's all good.
Yeah. All right. Yeah.
1, and then
This part right here, so 0.5 squared is 0.25, which is a fourth.
yes.
So 4 times a fourth is just 1, which is why it's just pi.
Yeah, I was just making sure that in those steps what you were doing was isolating DRDT.
Gotcha.
I wasn't sure what was going on.
Yeah, so what's funky about this process is like you are solving for d something dt as it's a variable, which looks weird, but it's just a variable. It's just a variable that changes per time versus one that's standard. Okay. So next one says the side length of a square increases at a rate of 3 inches per second. How fast is the area and perimeter of a square changing when with a side length of 5 inches? So step 1, let's find the area and perimeter formula for a square. So what would be that?
A equals B times H.
You're right, A equals B times H, but that gives me two variables. Yeah, so because with a square in particular, because it's not just a plain rectangle, with a square all the sides are the same.
Can you just do like B squared?
Yeah, exactly. So I'm going to use
Some variable squared.
exactly. So I'm going to say s squared. So base times height is correct, but we want to get as minimal variables as possible. It's going to make our lives easier, okay? So what would be perimeter?
Wasn't the one that would do something?
Perimeter, yeah, so you're right. Perimeter,
Or S.
yeah, so you're both right. So perimeter is usually 2 times the length plus 2 times the width.
Like
But-
something before.
Because all the sides are the same length, we can just say it's 4s, okay? I'm going to put the line through the s just so you differentiate it from a 5. You'll see. Okay,
My 5s and S's are the same, so I just read.
exactly.
I'm
Exactly.
confused.
So the side length of a square increases with a rate of. So is this giving you the side length of the square, or is it giving you the rate at which it changes?
The rate at which it changes.
So what would we call that?
Uh,
D,
dr over ds
yep,
over dt.
dt, yep. So that's the rate at which the side length changes. You see how it actually corresponds with the units? That's the side length is in inches and then the rate time. Okay, so this is a rate. Now we're talking about side length itself, which is what?
So your S is 5.
Your S is 5 inches. Exactly. So what we're now going to do is we're going to go through and think about this process. If my area is increasing, is my side length or my area going to stay the same at all?
No.
No. If my perimeter is changing, is my side length also going to change throughout the problem?
Yeah.
Yeah, so neither of these have constant variables in them. So for that reason, we're ready to differentiate. Okay?
Did
So what's the derivative of this going to be?
2S.
We got to do the other side first.
Oh.
Equals,
DOA over DT equals 2S times DS over DT.
good. And what about this one?
That is
Mm-hmm.
DP over DT equals 4 times DS over DT.
Good. So now that we have these, because remember we're solving for area and perimeter, it's like a double question. So we know what ds is, so we can plug it in. And then see how this one, you're basically done because there's no s left. But this one, however, you're also going to have to plug in the s.
Hey man, it's okay. It's okay.
So this is going to give me dA dt equals 2 times 5 times 3. And like I said, I like to put the units in at the end. So I know there's units on that. It's just easier to do it at the end for me. So this gives me dA dt equals 30. And dp dt equals 12. So now that we have these values, I'm going to go back and address the units. So we're talking about area over time. So area is going to be what?
Inches squared.
Good. Per what? Good. And perimeter is just going to be what?
12 inches
Inches per
per second.
second. So with perimeter is just a length. In reality, it's just 4 lengths added together. There's no squared units on that. And then don't forget, anything that's per time is going to be per time, whether it be minutes, seconds, hours, whatever. All right, so what I need you guys to do is flip your homework over. We're going to start the back number 2 together. Number 1 is pretty easy. I think you can all do that. But number 2, I just want to get you started on it, okay? So with number 2, this is going to address some geometry skills that you may be rusty on, so that's why I kind of want to address it. So it says a person is walking away from a lamppost. if the person is 5.75 feet tall and walks away from a 16-foot pole at a rate of 4 feet per second, what is the rate at which his shadow length is increasing? So this is the pole. This is the person. This is his distance from the pole, okay, which can change. That could be distance from pole. This is the shadow's length, which changes proportionally to everything else. Now, with this problem, what I'm going to do is I'm actually going to draw 2 separate triangles. So I'm going to do the big triangle and the little triangle. So I just find it easier to separate to understand everything. So this is the big triangle right here. So with the big triangle, we have the lamp post. Is the lamp post's height ever going to change?
No.
No, so that one we can put the value in immediately. So anything that's not going to change, you can put in prior to taking the derivative, okay? What is the length of this horizontal side? If it's x, this piece is x and this is s,
X.
x
Plus S.
plus s. Now the hypotenuse doesn't really come into play in this problem, so we kind of just leave it blank. Now we're going to then address the smaller triangle, which is formed by the person, okay? So as you can see, it's a smaller triangle. And then this person right here is our vertical height, which is what?
5.75.
Good. Now I know somebody could grow, quote unquote, but in the essence of this problem, is that ever going to
Well, I don't
change?
think he's gonna grow in the matter of seconds.
Exactly. I just have to say it because, you know, somebody will be like, he could change height. Yes, you're correct.
No brains.
Unless if he's old.
True. Brandon is not here today.
If he's old, he can change height.
True. But for the idea of this problem is his height isn't going to be a variable rate in the problem. Okay?
Yeah.
And then what would be this length right here?
S.
S. So about these 2 triangles, do you guys remember doing triangles in geometry where, okay, this is the reflexive property because they both have the same angle. And then this right here is, these 2 is a parallel lines cut by a transversal. So these 2 angles are also congruent because they're corresponding. And if 2 angles of 2 triangles are congruent, that means that the triangles must be what? They're not necessarily congruent, but they're what?
The same.
So if you had a model car and a big car, they have the same what? Proportions. Good. So they're similar triangles is what we would say. So as you can see, these triangles are obviously not the same size, but they are proportional to each other. Correct? So I can set up a proportion. So to set up a proportion, there's a multiple correct ways to set it up. So I'm just going to give you one of those.
Jesus Christ.
So the 16 on the big shape corresponds to the what on the other shape?
5.
75. Good. And then I have to do all the bigs on the top if I'm going to do it that way. So the x plus s, remember it's an s, not a 5, on the big shape corresponds to what on the little shape?
Yeah.
S. So you guys, the rest is going to be all you, but to start, they're giving you the rate at which he walks away, his rate of walking away from the pole. So this right here is going to be dx dt, okay? And you're trying to find ds dt. That's your goal. You're trying to find at what rate the shadow length is changing. Okay, does anybody have any questions about how I figured that out? All right, so you're going to cross multiply. You're going to simplify that down, and you're going to take the derivative, and then you can solve for the other variable. It's pretty straightforward once you get to that point. And that's that. You guys have the rest of the period to work on the homework.